The universe does not scream when its fate changes. It only leaves a faint mark in ancient light, hidden between galaxies, in the silent geometry of space. And now, for the first time, that mark may be telling us something terrifying. The force pushing reality apart may not be eternal. Imagine the universe as a vast dark ocean, where galaxies drift not simply through emptiness, but across the very fabric of space itself. They are not flying away from us like ships with engines. The space between them is growing, as if an invisible hand is stretching the canvas on which stars, nebulae, clusters, and black holes are painted. And for many years, the picture seemed almost clear. The universe was born in a hot beginning, expanded, cooled, created galaxies, stars, planets, life, and then it was supposed to move farther and farther into endless cold, not with thunder, not with fire, but in complete silence. The stars would go out, galaxies would disappear beyond the horizon of the observable world, and the distant future would become black, empty, and motionless, as if the cosmos were slowly forgetting that light had ever existed. But now, a crack has appeared in this picture. Not proof of the end of the world, not a cheap sensational headline, but a disturbing scientific hint that cannot simply be brushed aside. DESI, one of the most powerful cosmic mapping instruments of our time, has produced data that may mean something extraordinary. Dark energy, the mysterious force causing the expansion of the universe to accelerate, may not be constant. It may be changing over time. Its influence may be weakening. And if this is confirmed, the final fate of the universe may be completely different from what we imagined. Instead of galaxies drifting apart forever, we may face a halt, a reversal, and the collapse of everything that exists back into monstrous density, a scenario physicists call the Big Crunch. To understand why this is so important, we need to step away for a moment from the usual picture of space. We are used to thinking of the universe as stars, planets, comets, asteroids, gas clouds, and black holes. But all of that is only the visible foam on the surface of a much deeper ocean. Ordinary matter, the stuff our bodies, mountains, water, air, and stars are made of, makes up only a small part of the cosmic inventory. Most of the universe is hidden from direct view. There is dark matter, which does not shine, but holds galaxies in gravitational embraces. And there is dark energy, an even stranger entity that does not gather the cosmos together, but pushes it apart. It is dark energy that is connected to the accelerated expansion of the universe, discovered at the end of the 20th century through observations of distant supernovae. That discovery was like a moment when a person throws a stone upward and expects it to slow down under Earth's gravity, but suddenly sees the stone begin to accelerate more and more. Gravity should have slowed the expansion of the universe. All matter attracts all matter. Galaxies should have pulled one another back. But observation showed the opposite. Expansion was not slowing down, it was accelerating. That meant something else had to exist in the cosmic equation. Something invisible, yet dominant on the largest scales. That is how dark energy entered our picture of the world. The simplest explanation sounded almost beautiful. Dark energy is the cosmological constant, a property of empty space itself. Space expands, but the energy of emptiness remains constant in every part of it. The more space appears, the greater the total influence of this energy becomes. In this model, the universe is doomed to eternal acceleration. Galaxies will move away faster and faster. The sky of the future will become poorer. And after unimaginably distant ages, the cosmos will turn into a cold graveyard of extinguished stars and evaporating black holes. It is dark, but stable, terrifying, but calm. And now DESI brings us a hint that this calm may not exist. This instrument does not simply take beautiful pictures. It builds a three-dimensional map of the universe by measuring distances to millions of galaxies and quasars. You can imagine it as a giant time machine, not one that carries our bodies into the past, but one that allows us to read the history of the cosmos through light that has traveled toward us for billions of years. When we look at a distant galaxy, we do not see it as it is now, but as it was when its light first began its journey. The farther the object, the deeper into the past we look. DESI studies a special cosmic pattern, the trace of ancient waves born in the early universe. In the earliest eras after the Big Bang, the cosmos was a hot, dense, almost opaque sea of particles and radiation. Waves of pressure moved through that sea. Gravity tried to pull matter together. Radiation pushed it outward, and as a result, a characteristic scale remained in the distribution of matter, like a gigantic imprint of primordial sound. Today, this trace can be detected in the way galaxies are distributed across the universe. It is not sound in the ordinary sense. It is an ancient rhythm of matter, stretched by the expansion of space to a scale that makes the mind spin. Using this rhythm, scientists measure the history of the universe's expansion. Just as an archaeologist reads the traces of an ancient city from the remains of its walls, a cosmologist reads the fate of the cosmos from the positions of galaxies. And when the new DESI data were compared with other observations, a troubling possibility appeared. The model with unchanging dark energy may not be the best fit. The data begin to agree slightly better with the idea that dark energy evolves. In simpler words, it does not behave like an eternal, motionless constant. It may change over time. Here we need to be extremely honest. This does not mean that scientists have already proven the death of the universe. It does not mean that tomorrow the sky will begin to shrink and galaxies will fly back toward us. DESI's data on their own may still be compatible with the standard cosmological model. But when combined with other observations, a growing hint appears. The influence of dark energy may be weakening. And if the main engine of accelerated expansion is weakening, then the future of the cosmos becomes far less predictable. Imagine a train rushing across an endless plain. For a long time, we thought its engine would only grow stronger and that the train would never stop. But now, the driver notices that the engine's power is dropping. At first, only slightly. The speed is still high. The landscape is still racing by. But the principle itself has changed. If the drop continues, one day the motion may slow, then stop. And if somewhere ahead the track slopes back in the opposite direction, the train may begin to roll backward. For the universe, that backward is the Big Crunch. The Big Crunch is one of the most dramatic endings in cosmology. In this scenario, the expansion of space does not continue forever. It reaches a limit, like an inhalation that can no longer deepen. Then the reverse motion begins. Galaxies that had been moving away from one another for ages and billions of years begin to approach again. First slowly, almost imperceptibly, then faster and faster. Cosmic emptiness stops being a refuge. Distances shrink. The light of distant objects arrives more densely. The sky of future civilizations, if they ever exist in such an era, may become not darker, but brighter, more dangerous, more crowded. They would not fear emptiness, but an excess of light, heat, and closeness. In the early stages of such contraction, life might still be able to exist somewhere on islands of stability. But as space contracts, the temperature of background radiation rises, the dynamics of galaxies change, collisions and mergers become more frequent, star systems become less stable, orbits are disturbed, galaxies turn into chaotic fiery knots, black holes merge into even more massive monsters, and in the end, the entire history of the cosmos may be compressed back into a state of unimaginable density, where the familiar concepts of distance, time, and structure lose their meaning. Everything that was ever separate becomes one again. But the deepest anxiety here is not even this ending. The most astonishing thing is that we still do not know what dark energy is. We have given it a name, built equations around it, measured its influence, but we have not caught the thing itself. It does not resemble ordinary matter. It does not resemble light. It does not behave like gas or dust. It looks like a property of empty space, but that explanation immediately leads to enormous theoretical difficulties. Quantum physics tells us that emptiness is not empty. Fields tremble within it. Fluctuations appear and disappear. The invisible microscopic life of reality boils beneath the surface. But when physicists try to calculate the energy of such a vacuum and compare it with the observed dark energy, they get a monstrous mismatch. Not a small error, not a difference of 2 times, a gap of incredible scale. This is one of the greatest unsolved problems in modern science. And now imagine this. Not only do we fail to understand what this entity is, but we are beginning to suspect that it may also be changing. It is no longer just a background, not just a number in a formula. It is like an unknown character that had been behind the curtain all along, controlling the fate of the cosmos, and now, for the first time, has made a movement visible to the audience. Dark energy becomes not a motionless decoration, but an active mystery. And everything may depend on its behavior. Eternal cold, the big rip, the big crunch, or some other ending for which we do not yet even have the right image. Why does this discovery excite physicists so much? Because the standard model of cosmology has worked surprisingly well for many years. It explained the cosmic microwave background, the ancient light left over from the early hot universe. It explained the large-scale structure of the cosmos, galaxy clusters, and accelerated expansion. Yes, it had problems. Yes, there were tensions between different measurements, for example in estimates of the expansion rate. But overall, it was a powerful map of reality. And now a strange mark appears on that map. Perhaps the main component of the universe is not what we thought it was. At moments like this, science must remain cold. We cannot immediately jump to the conclusion. The universe will definitely collapse. That would be trash, not science. The data must be checked. We need new surveys, new measurements, independent methods. We need to understand whether an error is hiding in the processing, in the combination of different observational data sets, or in the assumptions of the model. Cosmology works with monstrous distances and extremely faint signals. Sometimes new physics really is knocking at the door, and sometimes it is just an old house creaking. But even the cautious version already takes the breath away, because if the hint is confirmed, it will not be a small correction. It will be a change in our understanding of the fate of everything that exists. Until now, we often imagined the end of the universe as a slow fading away. Now there is a possibility that the cosmos will not simply disperse but one day reverse. That the history of the universe may not be a straight road into cold darkness, but an arc, an inhalation and an exhalation, expansion and return, birth and collapse. And here an almost philosophical question appears. If the universe can collapse back, what happens after that? The end? A new Big Bang? A new cycle? A new reality born from the ashes of the old one? Science does not yet give a final answer. Near such extreme states, our theories begin to clash. General relativity describes gravity beautifully on large scales. Quantum physics describes the microworld beautifully. But together, they have not yet merged into a complete theory. That is why the final point of the Big Crunch remains a region where our knowledge grows dark. And still, the very possibility makes us look at the night sky differently. When you see the stars, you are not simply seeing lights. You are seeing a temporary chapter of a vast story. The universe is not a frozen stage. It evolves. It changes its tempo. It preserves traces of its childhood in the distribution of galaxies. It hides an emptiness and energy that we barely understand. And perhaps right now in the human era, a small instrument on Earth has for the first time caught a hint that the fate of the cosmos is not carved in stone. This makes our position both insignificant and magnificent. Insignificant, because we live on a tiny planet around an ordinary star in one galaxy among billions. Magnificent, because we, creatures made of carbon, water, and memory, have learned to collect ancient light, build maps of the universe, and ask questions not only about the past, but about the end of everything. We cannot stop dark energy. We cannot command space to expand or contract, but we can understand. And understanding is the most human way to touch eternity. Perhaps future data will show that dark energy is still constant, and the universe will continue its path toward a cold, endless future. Perhaps DESI's hint will dissolve like a mirage above a desert, but another possibility remains. We may be standing at the beginning of a new cosmological revolution, as deep as the discovery of the expansion of the universe, as frightening as the discovery of accelerated expansion, and just as beautiful, because it reminds us again, the cosmos is far stranger than any convenient picture we have managed to love. If dark energy has truly begun to weaken, this is not a reason for panic. It is a reason for wonder, for attention, for that rare feeling when a person looks up at the sky and understands above us are not simply stars. Above us is the living history of space and time, and its final chapter has not yet been written. Thank you for joining us on this journey into one of the most disturbing questions in modern cosmology. If you found this interesting, support the video with a like, and write in the comments which ending of the universe seems most likely to you. Eternal cold, the big crunch, or something completely unknown. Support the channel so we can continue exploring the deepest mysteries of the cosmos in a simple and vivid way. Stay with us, and see you next time.